Good afternoon or good morning, gentlemen, depending on the time you're watching this. The plan is that this is the last lecture until we will have our test. So it is a lot of information. That's kind of why I have a lot of stuff that you're going to be turning into me. However, I'm going to be talking about nuclear fission versus nuclear fusion. Your homework will be to complete a worksheet. With that worksheet, you'll be reading some scanned pages I have out of the textbook. I did try to scan them a little bit better, so hopefully they're a little bit clearer to read now. You also will be assigned your study guide, and then you're submitting a copy of these notes to me online on Canvas. I'm going to go in more detail about that towards the end, and I probably will do that in class. So it is important that you do take effectively good notes, especially because your test is open note. So you can use these. So first things first, we're going to talk about nuclear fission. Nuclear fission is actually something that we discovered by accident, which is really crazy to think about. Two German scientists were bombarding a uranium atom with neutrons. So what do you think that they thought would happen? Well, in this case, they probably thought that the uranium atom was going to get a lot bigger and be more unstable, and that's what they really wanted to accomplish. They found it out when they were trying to make atomic bombs. However, they found when they did this that they had created barium. So what had actually happened was that because they were adding more nuclei or neutrons in the nucleus, what was happening is that it started breaking down because it was radioactive and it didn't want to be unstable. It wanted to reach a stable state. So as they continued to add more and more and more, it continued to break down until we got all the way down to barium, which is 56 on our periodic table. Just crazy to think about. So the story of the nuclear fission is pretty easy. Is that number one, the greater force is the strong nuclear force, and that's what's holding together my protons. So as I continue to add neutrons, I noticed that I had a collision. So there's a critical deformation that occurs because I'm having too many neutrons. The neutrons are turning into protons. It's becoming unstable. It doesn't like that. So it starts deforming. Once it deforms, that great force is now an electric force, and that results in the splitting of the nucleus. So this is causing it to split. This is where kinetic energy is released along with 3 neutrons. So this is where some energy is released during the breaking in step 3. Doesn't happen in step 1 or 2, happens in step 3. Let me move myself down. I feel like I'm just going to be playing this game of where's Mrs. McCaslin going to be? Oops, there we go. Okay, so exactly how much energy is released in this deconstruction right here is that there's 7 million times more than an explosion of one TNT molecule. The energy that's being released is called kinetic energy. So this is a lot of energy that's releasing. If you think about it, think about a TNT molecule. It's really, really small, and it's 7 million times more than an explosion of one of them. Now, the fourth step, this is what happens as I start deforming, is that I'm releasing these 3 neutrons. So each of these neutrons are colliding with another uranium-235 atom. So this is where I get my chain reaction, where I just have a lot of breakage happening with my different uranium-235 atoms. So the fission reaction looks like this if I wanted to write it out. So I have a neutron, it hits a atom, hits an atom, breaks it apart, releases 3 neutrons, those go off, and the neutrons then go break 3 more uranium atoms, and then those have 9, and those break more, and then those have some, and then they break more, and that's where I get this big chain reaction. So the 3 neutrons is what's really important in understanding this reaction. So what does this look like in real time? So I have a simulation to kind of show you how fast that this is happening. You really don't need audio for this video, which is nice. So, just gonna take a second. There we go. So, here's what is 1, and now we're gonna look at if we had a lot, and we're going to get a visual of how quickly this chain reaction occurs, especially when we're using ping pongs. It reacts very fast. Here's a slow-mo to show you more of what it looks like without it happening in real time. It just, once it starts, it can't stop, essentially, until everything is broken down. So that's just to give you a visual on how fast this fission process happens. It's not a slow process. It's something that once it starts, it's very hard to stop until everything in like the path of destruction is gone in a way. So now, why isn't this happening all the time with all the uranium in our ground? If this is something that's happening very fast, you would imagine like, well, why isn't it continuing? Well, there's one reason, is that fission only occurs with our uranium-235. This is not going to occur with our uranium-238. So U-235 makes about 0.7 of uranium that's found naturally, whereas U-238 absorbs the neutron, it becomes stable. So that one's stable, that's what's in our ground. That's why we don't have this chain reaction happening all the time around us. Otherwise, it'd be very dangerous for us. So it's important to understand that it only happens in this fission process with 235. So that's just showing you how rare U-235 is. It is extremely rare to find. I mean, 0.7 naturally occurring, whereas U-238 has the 99.3%. Now, how do you think we create nuclear power at a nuclear power plant? Kind of feed for this, think about it. Nuclear power is the process. What process do all reactors currently use is nuclear fission. This is the process that we have in our nuclear power. And so when we're doing this, this is what it looks like, where we have our containment structure, we have control rods, we have pressurizers, we have steam, we have a lot of water going into this, we have turbines, generators, condensers, and that's where we get our power. The goal of this is to bring water using the nuclear fission to produce a steam to turn the turbine. So essentially, we're going to break it down. I'm going to move to the front, to the top, not the front. Is that part one, we have heavy water, which is deuterium, which is hydrogen 2, and it enters my fuel rods. So I have my heavy water here, and it enters in my control rods or my fuel rods here. The heavy water slows down neutrons, so they are more likely to hit and split U-235 atoms, because in this case, I really want to split U-235. I don't want to split other ones. And so after my water slows down, it starts hitting my U-235. The fission of U-235 atoms releases what we call thermal energy or my kinetic energy, and it heats up the heavy water. So I start having my reaction happen, it gets hot, and I start getting some steam. So my heat is transferred to water, and that boils my steam. My steam starts turning the turbine, and then the turbine creates an electromagnet that conducts electricity through copper wires. So my turbine helps a generator, and that's what gives me my energy. Things to note, nuclear fuel is mostly U-238 with only about 3% U-235. A nuclear bomb explosion is not really likely in the power plants, which is good because that means it's a little bit safer. The control rods actually limit the uranium fission rate and made of material that can absorb neutrons in slow fission, so that way we don't have anything dangerous happening. It's kind of a checks and balances. Here's a question for you. Now, we have nuclear fission going on, so does that mean the white gas chemicals and the chemicals and toxin that is being released in this gas is bad for us? The answer is no. That's actually the steam coming off from the water. The only toxic thing that you actually have from a nuclear power plant is the waste that's coming out with the water. So the steam's fine. The water, though, that's where the waste is, and that's where it's toxic. So think about The Simpsons. When they have fish swimming in the water, they have 3 eyes. However, it is safe to be around that steam that's coming out. Now we talked about fission. Let's talk about fusion. So fusion is different than fission. This is important to know. Fusion is when I have a combination between nuclei. So fission is my separation. Fusion is my combination. I'm taking them together. This will only happen at high temperatures. So these are like such as the high temperatures that are created by nuclear fission of uranium. But fusion cannot just happen. It has to be in a high temp. Lots of energy is released in here, and it is more powerful neutron that's coming out. So here's a little GIF to kind of show you fission or fusion. So fusion instead, I have two things happen, and now I have something new that's created, and I have a neutron being released. So these are where my bombs come into play a lot more. So here we go. So fusion bomb, for this to happen, stage 1 has to be fission. And it's with plutonium or uranium, so I have two. Those cores go through nuclear fission to create lots of heat. Now, so my plutonium, my uranium, they start breaking apart. They have the heat. This is where it comes in. Stage 2 is where fusion happens. This is where my deuterium or my tritium hydrogen, so my H2 and my H3 combine. They have fusion, and they fuse together. Stage 3 is my fission part 2, where stage 2 gives off one powerful neutron, and that can split my U-238 atoms. Typically, I cannot split U-238. It just will take in whatever neutron that comes at it. U-235 is where it separates. But in the fusion process, I have a neutron that's being released that is way more powerful, that can break my uranium-238. So that's the point of fusion, is I get something more powerful out after my combination to split something that I could not in fission. Now, there's some advantages and disadvantages for it. There's no size to limit. Hydrogen is much more plentiful than uranium, and so there's an advantage to that. However, the disadvantage is we really can't do that at this time. It is extremely difficult to do that. I do have a video to sum it up, and I'm going to link it onto the Canvas, so please watch it. This just kind of takes all the information that we just went over and discussed, and then I have more in your textbook questions. I just want you to have an understanding of fusion and fission, so hopefully that helps. However, this will be linked, and that's all I have for you. So make sure that you actually take the time, and let's go take a gander. Cool. At your daily agenda to talk about what you need to accomplish. Cool. So I have everything listed pretty well here. So I have the agenda, and then here's all the things that you need to complete. So you need to submit your notes to me. You need to complete the worksheet, read these pages here, and then also complete the Unit 4 study guide. In regards to the pages, excuse me, I tried to keep it pretty clear so that way you guys can easily access them. But if you have any issues reading them, let me know so I can kind of zoom in. But there's everything that you need to complete. For the submissions, I went into detail on Canvas on the assignment to really tell you, like, hey, this is what I want. So for the notes specifically, I have in detail here. So hopefully that helps. But if you have any questions, please let me know. Other than that, that's all I have for you. So if you have any questions, please let me know. And make sure you watch the video. I linked that to Canvas. So, all right.